confidence interval for a mean. Recall that the formula for a confidence interval is statistic plus or minus margin of error. When we are making an inference about a population mean, the statistic will be our sample mean, x bar. The critical value we will use to find the margin of error for our calculation will be based upon whether we know the population standard deviation or the sample standard deviation. When the population standard deviation is known, we will use the formula x bar plus or minus the z star critical value times sigma, our population standard deviation, divided by the square root of n. When it is unknown, we will need to find the sample standard deviation, s. Then we use the formula x bar plus or minus t star times s over the square root of n. T star is the t critical value. This is different from our normal distribution. It's based on something called a degrees of freedom as well. Our degrees of freedom for a single mean confidence interval is n minus 1. So t star comes from a t distribution, but what is a t distribution? It's bell-shaped like a normal distribution, but it's not quite the same. So the blue represents our standard normal z distribution. T, as we have more and more degrees of freedom or larger and larger n's, becomes closer to normal, but smaller values of n flatten it out. Finding the critical t value for a confidence level, CL, and df degrees of freedom, remember our degrees of freedom is equal to n minus 1, is found by QT in RStudio or inverse t, INVT, in the calculator. What we put into our calculation is the same as what we did when we were doing it with the standard normal. Confidence level plus 1 minus confidence level over 2, but now we have to add our degrees of freedom. The assumptions for a population mean are that the sample must be from a simple random sample of the population of interest, and the data must come from a normally distributed population. If it's not normally distributed, or we're unsure if it's normally distributed, the sampling distribution of our means must be normally distributed. Remember, we said that when we have a sampling distribution of x bar, that it can be considered normally distributed if n is greater than or equal to 30. Let's work some examples. Suppose your class is investigating the weights of Snickers 1-ounce fun-sized candy bars to see if customers are getting the full value for their money. Assume that all the weights are normally distributed with a standard deviation of 0.005 ounces. So this value right here is our population standard deviation. So sigma is 0.005 ounces. Several candy bars are randomly selected and weighed with sensitive balances borrowed from the physics lab. We get the following results. We have 1, 2, 3, 4, 5, 6, 7, 8. N equals 8. We want to determine a 90% confidence interval for the true mean. Now we're told that this is normally distributed, so we're okay with a size of 8. Our sample mean would be found by taking the mean of these values right here, adding them up and dividing by 8. When we do that, we get a sample mean of 0.995. Now, since we have this population standard deviation, sigma, we'll use z star for our critical value. Z star for a 90% confidence interval will be equal to inverse norm of 0.9 plus 1 minus 0.9 over 2, which is 0.95. This is 1.645. Our standard error or standard deviation calculation here will be sigma over square root of n. So the margin of error is the product of these two, which is 0.0029. This makes our confidence interval 0.995 plus or minus 0.0029. This gives us the interval from 0.9921 to 0.9979. So what this means is if we repeated our sampling, approximately 90% of our samples will contain the true mean. In other words, we're 90% confident that the true mean weight of the Snickers candy bars is between 0.9921 ounces and 0.9979 ounces. Next example. A simple random sample of 16 seniors from HISD had a mean SAT math score, so this is from the sample that makes X bar equal to 500, with a standard deviation, again talking about the sample here, of 100. We know that the population of SAT math scores for the district is normally distributed. Now, since we don't have the population standard deviation, we have only the sample standard deviation, we will use T star for our critical value. We want to find the 90% confidence interval. So the T star, we will do inverse T or QT of 0.95, comma, our degrees of freedom, which is n minus 1, 15. Again, the 0.95 comes from 0.9 plus 1 minus 0.9 over 2. Now, when we calculate this value for our T star, we get 1.753. That's my critical value. So my confidence interval will be my sample mean plus or minus this critical value times our standard deviation over the square root of n. This makes my margin of error 43.825. So my confidence interval is 456.175 to 543.825. So we're 90% confident that the true mean SAT math score for seniors in this HISD would be between 456.175 and 543.825. In other words, if we took, say, 100 repeated samples and did 100 confidence intervals, 90 of those 100 would contain the true mean SAT score. Example 3. The effect of exercise on the amount of lactic acid in the blood was examined in an article for Exercise in Sports magazine. 8 males were selected at random from those attending a week-long training camp. Blood lactate levels were measured before and after playing 3 games of racquetball, as shown in this table. Use the data to estimate the mean increase in blood lactate level using a 95% confidence interval. Now the key word in this problem is that we're looking for the mean increase in the blood lactate level. So to figure out the increase, it will equal our after values minus the before values. So let's subtract those in our chart. Once we get the increase values, we'll find the mean increase. The mean of these values that I've written below, the mean increase, is 13.625. Now we're not told anything about the population. And because we have only 8 pieces of data here for our sample, we would have to assume that our population is normally distributed. So we need to compute our sample standard deviation, and that would be 8.2797. Again, we don't have the population standard deviation, so we'll need to use the t-distribution with 7 degrees of freedom. So we'll use inverse t or qt. We want a 95%, so this will be 0.975. 95% plus 1 minus 95% over 2, comma 7. This gives us a value of 2.365. So my confidence interval will be 13.625 plus or minus 2.365 times our S divided by the square root of n, which is 8. This will give us the confidence interval of 6.70 to 20.545. In this last example, we want a confidence interval of 95% for the mean of a population. We want it to be accurate within 0.3 units. A sample standard deviation is 2.9. Find n, the sample size that we need to have our desired accuracy. Well, it's 0.3, that's my margin of error. Now, since we have the sample standard deviation, we would normally use t star. However, we don't know n, so we don't have a value to put in for degrees of freedom. That means we'll have to use a z star for a 95%. The z star for a 95% confidence interval will be 1.96. So our margin of error has to be greater than or equal to our margin of error calculation, which is our critical value times the standard deviation over the square root of n. Now I'm going to multiply the square root of n to the other side and divide the right side by 0.3. So that gives me the square root of n has to be greater than or equal to 18.9467, and I square both sides, and I get that n has to be greater than or equal to 358.98. Now remember, this is a greater than or equal to, so we always round up. So our smallest sample size would be 359.